Hello and welcome to video 2 of 3 for chapter 8. Now in the previous video I defined capacitance and showed you how it arrives, or at least it arises, naturally from geometry. When you look at the field that sits between two objects, two metal pieces of metal, we'll say. One of the examples that I used was parallel plates. Another example were concentric spheres, and the last example that I used was a coaxial capacitor, which I, pointed out was basically what cable is, for like cable TV. Now, um, in this video, what I'm going to start talking about are components that we see inside circuits, specifically electrical circuits. So electrical circuits usually have some sort of power source, and what that power source does is to use conductors like wires to deliver electrical energy to components which may individually do things that are useful for us, or as a whole do things that are useful for us. Now, that said, the most common power source that you see used in electrical circuits are batteries. Now, batteries are sources of what's called DC voltage. DC means direct current. We are not going to define this yet. We will actually be defining this the next chapter to 2. So, the important thing is that the current, or not the current rather, but the voltage that they supply is constant. It doesn't change. Now, batteries also typically are electrochemical in nature. They use, a combination of chemicals, perhaps, some sort of acid and dissimilar metals, which a lot of times are called cathode and anode. And what they do is to, if you think sort of like, of a car battery, if you think of a car battery, where you have two terminals, one's positive and one's negative. What they do is to generate an electrical potential difference between the two terminals. And it's this difference in potential between the posts that we think of as voltage. Now remember, we define voltage as being the electric potential at a point in space. But in circuit analysis, and in most electrical applications, when they use the word voltage, they don't mean at a point in space. They mean the difference between 2 points in space. Okay? So here, for example, a 12-volt battery, which is what you see commonly used in cars, that means that if you were to look at the voltage potential difference between these two, you would have 12 volts. This, for example, could sit at 1,000 volts, and this could sit at 988 volts. When you look at the difference between the two, you get 12 volts. Now, so the symbol that you see used in an electrical circuit for a battery looks a little bit like this. You have a long bar, and then you have a shorter bar, and these bars are connected to the wires in your circuit. So these would be wires, and this right here would be your battery. Now, the length of the bar tells you whether you're dealing with a positive or a negative voltage. And that's because positives are bigger than negatives. So the long bar is the positive side of a battery, and the short bar is the negative side of the battery. Now, if you were to go back and think about some of the stuff that we mentioned specifically in the Gauss's law section, you might recall that I had mentioned that when you look at conductors and you use Gauss's law there, that you had a series of properties. Now, one of the properties was that the electric field near the surface of a conductor always points straight out, and it's constant magnitude if you have a constant distribution of charge on the surface. We're going to assume for the moment, specifically in the case of DC circuits, which are going to be what we're going to be dealing with for quite some time, that the charge that's distributed on your wire is constant. The electric field as a consequence is constant. So if I were to move charge on the surface of this wire, you'll notice that the direction of motion is perpendicular to the electric field, which means that the work that's required to move this charge is zero when it comes to fighting with the electric field. Now, there may be other properties, which we'll be talking about in the next chapter, specifically resistance, that hinder your ability to move charge. But here, what we're assuming is that our wires are regions of equipotential. All conductors are regions of equipotential. Now, what does that mean for us? Well, the positive side, for example, of this battery, we'll say sits at 1,000 volts. And the negative side, again, maybe sits at 998 or 988 volts. The difference between them would be, again, 12 volts. If I were to extend this wire over here and hook it to some sort of component, we'll say like a computer or something like that, and then I extended this wire over here and hooked it to the other side, what I'm doing along this conductor, which is what a wire is preserving the amount of voltage such that at this point right here there would be 1,000 volts sitting there. Equipotential, equal potential, the potential does not change. On this side, there would be a negative 988 volts, and across my device, just like across the terminals of this battery, I would see 12 volts. That's how equipotentials work. Now, so as I mentioned, last time, capacitors store charge, and as a consequence, they store energy. So, and it takes work to put that charge in there. So, as we had, mentioned, there's a relationship between the amount of charge, the capacitance of your capacitor, and the available energy that you can use to put the charge onto your capacitor. So, if you were to think of a configuration like this, for example, where you have a battery which has a voltage, I'll say a V, and you have a positive side over here and a negative side right there. This positive is going to be conveyed over here, and this negative is going to be conveyed over here because it's equipotential. Now, electric fields point from low voltage to high voltage. Now, is that right? That's not right. Now, so electric fields point from high voltage to low voltage. Okay? You can see that, if you look at the equation, delta V is equal to minus. I'm going to assume that everything here is constant. E, dotted with delta R. So, for example, If you look here, I think we can agree that this is the high voltage part and this is the low voltage part. So this would be V minus V naught. Let's just pretend that V is the positive and V naught is the negative. Okay, so that's on the left-hand side. On the right-hand side, our delta R is going to be the distance between the plates. Okay, so when I do this difference here, I would need to get a positive number. So if I were to look here, again, V naught is here, V is there. This would be the direction that we would integrate or we would walk. This is the direction of delta R. Okay, would be that way. So in order to make this be positive, with this minus sign hanging out in front, and knowing that this points this way, I would need that this dot product right here to give us a negative. So you have a negative times a negative makes it a positive. Well, if you look here, if this is the direction of delta R, then that means that my E would point this way. It points from high voltage or high potential to low potential. So this right here is the direction of E. I'm just going to get rid of this so there's no confusion as to what this is all about right there. And, what happens here is that, you have this electric field that's constant. This is between these plates. And, we know negatives like to go against, the electric field. So you accrue a bunch of negative charge here. And what this negative charge here does is to push the negatives that are here away, basically this way. And so that gives you a glut of positive here. And, for every Q that you see here that's negative, you have an associated positive Q that sits up here. And so, how much charge is there? Well, that's equal to C times V. So what batteries do is to give you the potential energy, the electrical energy that's required to get these charges to move. And as a consequence, the work that's done moving these charges ends up getting stuck inside the capacitor, which we're going to discover in video 3 is stuck inside the electric field that sits between the plates of the capacitor or the spheres or the cylinders. So just as a simple example, how much charge is stored in a capacitor that is in series with a 12-volt battery if the capacitor has a capacitance of 1 microfarad. Now, a microfarad, which we typically write the following way, mu times F, is about right for the realm of your average capacitor that you see. 1 farad of capacitance is a tremendous amount of capacitance. Microfarads are pretty common, ranging upwards typically in a circuit. So if you take a look here in our little circuit here, this is very clearly a battery. You have a plus side and you have a minus side. Now this says that the capacitor is in series. In series is a big hint with the 12-volt battery. So what that does is to give us an idea of how many volts our battery is. And the word in series means the following. That means that if you look at how things are connected inside the circuit, it's one connected to another, is connected to another, is connected to another in sequence, in series. Now, here you'll see something that has 2 parallel lines or plates. This is the symbol right here that's commonly used for a capacitor. Okay, so this is the capacitor symbol. Now, again, the properties of a capacitor that we're interested in are its capacitance, C, and here it's 1 microfarad, and micro is 10 to the minus 6. And what we want to do is to find out how much charge is stored in here. So we're going to use Q is equal to C times V for that. C is 1 times 10 to the minus 6, whoops, 16th, minus 6 farads, and our voltage is 12 volts. So were I to stick this in a calculator, very simple, 1.2 times 10 to the minus 5th. Coulombs. if I wanted to stick with sig figs, technically it would be 1 sig fig. So that would be 1 times 10 to the minus fifth. So, now let's talk about what happens when you have more than one capacitor. This is another example of a series circuit. Okay, we have a battery, which I'm going to say has a voltage of V. This is the positive side, this is the negative side. And we have 2 capacitors, which are potentially of different capacitance. I'll say this has a capacitance of C1, and this has a capacitance of C2. Now, remember, voltage is kind of like electrical potential energy. Okay, we've just taken the Q out of the equation. So if we think of it as energy, we know energy is neither created or destroyed, it's only transformed, right? So if I were to follow the equipotential rule and think of this wire right here as being a region of equal potential, then whatever voltage this is going to be the same voltage that sits here. And whatever voltage this is going to be the same voltage that sits here. Now, the way a capacitor is drawn is deliberate. There's nothing that sits between the plates. There's no connection between this side of a capacitor and this side of a capacitor that's direct. It has to go through a battery or some other component, at least as drawn. So for every little plus right here that you have, you're going to have an accompanying minus that's there. Just like what we had talked about when we were talking about this right here. But if you look over here, this bit of metal sort of dangles free. So if I were to pull a negative into this plate right here, it has to come from somewhere. And it's going to come from over here, so there'll be a positive, which as a consequence is going to induce a negative here. And what you'll discover here is that for every positive you have here, you'll have a minus here. And for every minus here, you'll have the same positive here. And for every positive here, you'll have a minus here. And what that means is that this capacitor here has a charge of Q in it. And that's going to be the same as the charge here. But look, right? So if I were to take this center piece and pull it out, overall, they would have a charge of Q as well. Okay, so in a series circuit, the charge across the capacitors is all the same. So if you think of Q equaling C times V, if Q is the same here, but C is different than this one, then that means that V would be different as well. But according to the rules of conservation of energy, if I were to look at those V's, they would have to add up to what went in. So this is actually a general rule in a series circuit that voltages add. This is one of Kirchhoff's rules. This is one of Kirchhoff's voltage laws. This is for series circuits. Now, so, one question we might ask is, what is this charge Q here? And the way to answer that type of question is to reduce circuits in complexity until you get to the most basic configuration of all, which is one in which you have one capacitor in it. So what we want to do is to sort of figure out how to combine these 2 capacitors together so that the circuit ends up looking something like this right here, where you have the same electrical potential, the same voltage. You have the same Q overall that's being stored, but you have what's called an effective capacitance that gets you there. So what you're doing is you're reducing in complexity from 2 components in line with the battery to 1 component. Now, this new circuit with the effective capacitance has to obey the same rules here, which means that, for example, if I were to look here and note the fact that Q is equal to C1 times V1. And I were to note the fact here that Q is equal to C2 times V2. Well, here, Q, the same Q, because remember it's the same across both, is that going to equal to C effective times the voltage across that, which would be V overall. Okay, so how do we get from here to here? Well, we're going to use Kirchhoff's voltage law. So Kirchhoff's voltage law says that if you have a bunch of components in series, all you do is you add up the voltages across them. Or better yet, those voltages are distributed across each component this way. Here we only have two. V is equal to V1 plus V2. But we have relationships between Q, C, and V. Specifically, V1 is equal to Q over C1. V2 is equal to Q over C2. And we also know from the reduced circuit we're trying to get to that it should be true that V is going to equal to Q over C effective. Okay? So when you plug this into this, you get Q over C effective is equal to Q over C1 plus Q over C2. Now the Q's are all the same. They cancel. And so what we have here is a rule for adding capacitance. They add inversely. Okay? Now, so that's a series circuit. Well, there's another type of basic circuit that you see, and that's called a parallel circuit. And in a parallel circuit, the way to think about it is that the way the wires are connected to your devices makes your components inside your circuit, if you were to sort of block them out like this, look like they're parallel to each other. So it's not one after another, after another, after another. Parallel circuits are very useful in that, just to give you an example, if you've ever strung up Christmas lights or lights that are strung in tandem, most lights are in series, so if one light blows, your entire string of lights stops working. But in a parallel circuit, if one component goes, the other one is still connected to the battery because it doesn't have to go through its neighbor to get there. A good example of a parallel circuit would be your electrical outlets in your home. If you look at your standard receptacle in your house, you have two plugs there. So let's pretend that you plug in, I don't know, a stereo into one and a TV into the other. If I unplug the stereo, the TV doesn't, just stop working because there's no way for the electricity to get down to the bottom outlet or something like that. So those are wired in parallel because, you want it to be such that if you shut a device off, all of your devices don't go off. So here, just like before, here's our battery. This is the positive side. It's got the long bar. You have the negative side, which is the short bar. It has a voltage, I'll say a V. And remember, batteries are regions of equipotential. So if this is positive, this is positive, this is positive, this is positive. So these wires, regions of equipotential. So this is all positive right here. And so you have your negative right here. This is negative, this is negative, this is negative, positive. This is negative right there, this is negative. This is all negative, right? So what that means is that across this capacitor right here, you have the same voltage that you see at the battery. And across this capacitor right here, you have the same voltage that you see across the battery as well. Potentially these are different devices. And what we want to do is play the same sort of game. We want to reduce this in complexity to turn it into, a one capacitor circuit so that we can find, rules with respect to addition and stuff. So our voltage doesn't change, and, we're going to get some sort of C effective right here with a charge of Q. Now that said, remember the relationship between capacitance, charge, capacitance and voltage. It looks like this. So here, Q is going to equal to C effective times V. But if you look at these right here, unlike the previous example where, we don't have a connection, between our capacitors on this side, that's not true for a parallel circuit. So what that means is that our voltages don't add; they're the same on both of them, and so with different C's, we have different Q's. But here's the thing: a Q is a charge. A charge is a tangible thing. So if I were to add up the charges here and add up the charges here, they better equal to whatever it is that's going to go onto this. So it must be true that the total charge is just equal to what you get when you add up the charges on all the capacitors in a parallel circuit. Q is equal to C effective times V, so that would be C effective times V is equal to Q1. Q1 is equal to C1 times V. Q2 is equal to C2 times V, since the voltage is the same. And the V's cancel because the voltages are all the same. And now we have a rule for adding capacitance for capacitors that are in parallel. And that's that your effective capacitance is equal to, you're just adding it up. Now, what I pointed out here with respect to the voltage, that's actually another one of Kirchhoff's laws. So here, Kirchhoff's voltage law for series circuits says that you add up the voltages. The one for parallel circuits, in a parallel circuit, the voltages are the same. It's the same across all components. Okay, so examples. Let's see here. So what I'd like to do is to look at two capacitors that are in series and then look at them in parallel. And I just want to see how the capacitances add. So I'm going to freehand this. For series, let's pretend that you have some sort of positive side, some sort of negative side like that. We're just adding capacitances. So if it's in series, you have your capacitor here, then you have your capacitor here, and then maybe that goes to a battery or something else like that. Now I'm going to call this C1 and this C2. And let's pretend that C1 is 2.0 microfarads. And we'll pretend that C2 is 3.0 microfarads. Now in series, we know that to get the effective capacitance, what would these two act like if they were just one? That you add them inversely. So if I were to solve for C effective here, it would be 1 over C1 plus 1 over C2. Now what's C1? 2.0 microfarads. What's C2? 3.0 microfarads. Now what I'm going to do is to find a common denominator and add them. I find personally that it's a lot easier for me to work with fractions when I'm dealing with capacitance. So here the common denominator is 6. So if that were the case, that would make this 3, and this would be 2 for a common denominator of 6. And so 3 plus 2 is 5. This would be 5/6 or 6/5 when you flip it. So this is 6/5 microfarads. And what I'd like to point out here is that 6/5 is just a little bit bigger than 1. So C1 and C2 are all above 1. This is just a little bit bigger than 1. And when you add capacitors together in series, what you end up with is an effective capacitance that's usually less. Okay, so it's one way to reduce capacitance, which is one of the reasons why we're interested in these addition rules. When if you were to go to an electrical component store and buy capacitors, the capacitors that you would get would be of standard size, and 99.9 times out of 100, what you're stuck doing is trying to figure out how to fit a whole bunch of standard capacitors together to get you the capacitance that you want, which is usually something that's non-standard based upon the design of your circuit. Okay. Now, so if I were to work the same problem, except now work it in parallel it's going to look like this. So here, when you add them together to get the effective capacitance, you literally just add them. C effective is C1 plus C2. 2 plus 3 is 5. Okay. So, sometimes what we do is to add capacitors together in combinations of series and parallel to sort of fine-tune to get exactly the capacitance that we're looking for. So what I'd like to do is to do, 2 quick examples just with different capacitances of ways that things can be put together. And I'm going to show you how you reduce them in complexity to get the effective capacitance. So I want you to think of a circuit. We'll say maybe that this side is positive and this side is negative. It really doesn't matter. Like I said, we're just adding these things together. And maybe your hybrid circuit. And by hybrid, I mean that it's a combination of series and parallel capacitors. Maybe it looks like this. It's not a very good line. Maybe there's one right here. So I'll call this C1, I'll call this C2, and this C3. And let's pretend that C1 is 2.0 microfarads, C2 is 3.0 microfarads, and we'll say C3 is the same thing as C2. Now, the way you add these things together to get an overall effective capacitance, that is, you want to make this thing look like it's just, one capacitor, is, let's see, effective, is to reduce them in complexity in a series of steps. For example, I can't treat this as though it's a parallel circuit because I have these two right here that are in series. So maybe what I'll do is I'll go from this to something that looks like this. Now what I'll do is I'll use my rules for adding capacitors in series to find what we'll call C23, which is the effective capacitance for these two. I still have C1 here, and now it's just taking and adding these two together in parallel to get, our effective capacitance like this. So you do it in a series of steps, okay? So to get from here to here, what we need to do is we need to add C2 and C3 together. But C2 and C3 are in series. Now remember, the rule for adding two of these things together in series is that your effective capacitance, which I'm going to call again C23, is going to be 1 over C2 plus 1 over C3. Now, again, in this case, RC2 is 2.0 microfarads, and RC3 is going to be 3.0 microfarads. And as I pointed out, in this problem right here, when I added these things together in series, you get 6/5. It's the same idea. So in this particular case, C23 is going to be 6/5 microfarads. Okay. So what that does is to reduce it to this. Now to go from here to here, we have to add them in series, or rather in parallel. And in parallel, we know that our effective capacitance is going to be what you get when you take C1 and you just add it to C23 because they add together just straight up when you do them in parallel like this. So C1 was 3.0 microfarads. C2 is 6/5 microfarads. Again, we could play the common denominator game and just add them that way. In fact, I think that's what I'm going to do. Common denominator would be 5. 3 times 5 is 15. 15 plus 6 is going to be 21. So that would be 21/5 microfarads. Or, again, if you were insistent in, expressing this in fractional form, it's going to be something like, what, 4.2 maybe, I think? 21/5. Yeah, 4.2. So, 4.2 microfarads there. So you start with a complex circuit, and then what you do is you break it into, using rules for addition for series and for parallel, into less and less complicated things until you get it to this. And then you can work backwards if, for example, you had a question like, what is the charge across each one? What is the voltage across each one? Which we're going to do an example of that here in a bit. Let's look at an even more complicated circuit. What if your circuit looks like this? What if you have a capacitor here? And you have a capacitor here. Maybe you have two capacitors here. I'll call this C1, this is C2, this is C3, and this is C4. And, maybe C1 is, 1 microfarad. C2 is 2 microfarads. C3, 3 microfarads. And C4, 4 microfarads. Makes it easy. Well, again, this looks pretty complicated. But I can kind of see the steps that I want to do. So the first thing I want to do is to take these two that are in series and turn them into one. So our first reduction in complexity is going to look like this. Where this is C23, this is C4, and this is C1. Now you can see our next one. Our next one is going to be to take these two right here and turn them into one. When you do that, what that does is to make this act like it is in series with this. So this would be C1, and this would be C234. Then our last reduction in complexity is going to be taking these two and turning them into one. They're in series with each other, so that's pretty easy. You already know how to do that. And now we have our effective capacitance. So it's going to be a 3-step process. Step 1, Step 2, and then Step 3. So let's start with Step 1. Step 1 is taking C2 and C3 and adding them together to give us C23. Now, C23 here is, since they're in series with each other, is going to be 1 over C2 plus 1 over C3. C2, I feel like I've done this before. I have. You know, we did it here. We did it here. 2 and 3. So now I have C23. Awesome. So now let's take these two right here and combine them into one to make C234. Well, C234 is what you get when you take C23 and you add it to C4. Well, C23 is 6/5 microfarads. C4 is 4 microfarads. The common denominator here is 20. Okay. So that would make, this would be 6 times 4, which would be 24. This would be, 4 times 5, which would be, hold on, is that right? Common denominator 5. Oh, hold on. I'm getting ahead of myself. That's silliness. It's not 20. It's just 5. There. That's better. So, there you go. 26 fifths microfarads. That's going to be what? 5.2, I think. Yeah, 5.2. So there you go. 5.2 microfarads. So this is C234. Now we're going to add C1 to C234 in series, that is using something that looks like this, to get C effective. So C effective here is going to be 1 over C1 plus 1 over C234. Now C1 is 1 microfarad. Let's see. I'll go ahead and do the 26 fifths representation. Whoops. So the reason why is because 26 fifths is going to become 5/26. So you'll have 1 plus 5/26. This would be 26 over 26. 26 plus 5, 29. Or actually 31. 31/26. Here, when you do that addition, and you flip it up, it becomes 26 over 31. So this one, because of that 31 sitting there, is not very nice. So 26 divided by 31 is 0.84. Or, something like 0.8-ish microfarads if you want to, keep to 1 sig fig here. So, as you can see, the process here is reduction in complexity, and then if you need to, you can work backwards using the relationship between Q, C, and V, and knowing the rules for series and parallel circuits to figure out what the voltages and the stored charge would be. Just as a simple example, I want you to think of a situation like this, where we have, well, that got there. Let's get rid of that. So let's pretend that we have a battery here, and the battery goes to two capacitors that are in series with one another. So let's pretend we'll call our battery V. This is C1 and C2, and this is what we've been given. Our battery is 125 volts. C1 is 3.0 microfarads, and C2 is 5.0 microfarads. So what I'd like to find here is the voltage across C1, the voltage across C2, and also the stored charge Q. Okay? Now, so remember, this is a series circuit, and we know a few things about series circuits. First, the voltage is add. Okay, this is true. Second, Q is the same on everything. So if we can find the Q across this one or the Q across this one, we're set. We're okay. All right. So to solve this, typically what you do is you reduce this in complexity until you have one component. You find Q. And then knowing Q, you can use Q is equal to C times V to find the voltages across each one of these. Okay? So when you reduce this in complexity, your C effective, since these are in series, looks like 1 over C1 plus 1 over C2, which is going to be 1 over 3.0 microfarads plus 1 over 5.0 microfarads. Well, again, the common denominator here is going to be 15. This will be 5/3, or 5/5 rather. This will be 3/5. 5 plus 3 is 8. Oh, don't need to do that. And when you flip it, it becomes 15/8. So, put that in your calculator. 15/8 is about 1.875. All right. Let's see here. Now, so reducing this in complexity, now you can use this, right? Now a micro is 10 to the minus 6. This is 125 volts. You get 2.34 times 10 to the minus 4th coulombs. That's our Q, since the Q is the same across all components. Now, what about the V's? Let me just box this real quick to keep track of it. Well, Q is equal to CV, which means that V1, for example, would be Q over C1. .0 times 10 to the minus 6 farads So if I were to divide this by 3 times 10 to the minus 6, I get something like 78.125 volts. Okay. Now, V2 is going to be Q over C2. Same Q. C2 is 5.0 times 10 to the minus 6 farads. So let's see what you get here. .875 volts. Now watch this. The way to check it is to see if this holds true. So when I add this to this, I should get 125 volts. And sure enough, when you add 46.875 to 78.125, you get 125. So we found the voltage across both of the components, and we found the charge on the components as well. Now, let's do another example. So we'll do a more complicated one now. Imagine a situation where you have your battery right here. You have two components like this that are in parallel to each other. Like this. And then you have it going up to your battery there. So there's V. I'm going to call this C1. I'm going to call this C2. I'm going to call this C3. Let's pretend our voltage here in this case is 15 volts. Okay. We'll say C1 is 2.0 microfarads. We'll say C2 again is 2.0 microfarads. And I don't know, C3 maybe is 4. So what I like to do is to find V1, V2, V3, Q1, Q2, and Q3. So find all of the voltages and all of the charges. Now you have a hybrid circuit here. These guys right here are in parallel, and this is in series. So you can, see where this is going to go. We're going to reduce this in complexity. Our first step is going to be a battery hooked to a capacitor called C23, which goes to C1, back into the battery again. Then to C effective. Like that. So, let's go to our first step, and that's adding C2 and C3 together. Well, C2 and C3 are in series. So we know that or in parallel rather, and we know that capacitors that are in parallel, you just add their capacitances together. So C23 here is going to equal to C2 plus C3. C2, 2, C3, what did I call that? 4. 3. C3 is 4. 4 plus 2 is 6. All right, so that's easy enough. The next step is to take and add C23 and C1 together. Those add together in series, which means that it's an inverse thing. So, if we do that, C1 is 2.0 microfarads. C23 is 6.0 microfarads. The common denominator here is going to be 6, which means that this is going to become a 3. 3 plus 1 is 4. That would be 1 over 4 over 6 microfarads, or 6/4. So this is C effective. Now we can use Q is equal to C effective times V. We know V is 15 volts. This is going to be 6/4 times 10 to the minus 6 farads. When you do that, I get 2.25 times 10 to the minus 5th. So that's how many coulombs our C effective capacitor has, or is storing rather. But it's stored differently. Some of that charge is going to be here, and some of the charge is going to be in these guys as well. Now let's remember how charge works whenever you're dealing with capacitors. So if you're dealing with a capacitor that's in series, the charge across C1 and the charge across C2 is the same, and that happens to be the same thing as C effective. But as we mentioned with parallel circuits, it's not the same. So you'll have a Q1 here, a Q2 here, and then those are going to add up to your overall stored in both. So if you're to look, for example, at this would be Q2, this would be Q3. This we'll call Q1, but Q2 and Q3, because they add together and give you something that looks like it's in series like this, those are going to equal to Q1. And this C effective is going to equal to Q1. Okay? So, this right here is going to be the charge that's on this, but it's also going to be the charge that's distributed across both of these. Now, so that handles Q. Now let's take a look at this reduction in complexity right here. Because we know the voltage here is going to be here, and is also going to be here as well. And it should be that V is equal to V1 plus V23. So, Q is equal to C times V. Q1 is equal to C1 times V1. V1 is going to equal to Q1 over C1, or (2.25 times 10 to the minus 5th coulombs divided by C1, which is 2 microfarads. So if you do that, that's 11.25 volts. So we know in a series circuit that this voltage here plus this voltage here equals this voltage here, which means we can immediately find V23. That's going to be the total voltage minus whatever V1 is, which is 15 volts minus 11.25 volts, or 3.75 volts. So we found V1. So Q1 is this. Let me wipe this out right here. V1 is this. This is V23. V23. Now what's V23? Oh, that's the voltage across these right here. Now if I remember how voltage works in parallel circuits, the voltage that's across here is the same as the voltage here, is the same as the voltage here. We just found V2 and V3. Ah, okay. We have Q, V1, V2, V3. Okay, so now if I remember correctly, Q is equal to C times V, right? So if I wanted to find Q2, for example, or Q3, for example, Q2 would be C2 times V2. What's C2? 2 times 10 to the minus 6 farads. What's V2? Well, we just found that, 3.75 volts. So, 75 times 2 times 10 to the minus 6. 7.5 times 10 to the minus 6 coulombs. Q3 is C3 times V3. C3 is 4 times 10 to the minus 6. V is the same. (1.5 times 10 to the minus 5th). There you go. So in general, excuse me. So in general, the way this works is that you take your circuit and you reduce it all the way back to what it would be like if it only had one component. And then you work forward from that in steps to get you back to your original circuit. And in each step, what you do is you find all the quantities that you can. Here, with a capacitor, you can find charge and voltage. And, in the study of electronics and stuff, we call this solving a circuit. So this is how you solve a circuit. Now, in the third video, we're going to talk about something called dielectrics, which is what happens when you add an extra level of realism to capacitors. And we're also going to talk about where the energy is stored at inside a capacitor. And I'll see you then.